When agents run code, commands, queries, or API calls, small mistakes can become system-wide incidents. Sandboxing creates enforceable runtime boundaries, limiting files, network access, time, and failure behavior, so dynamic actions remain useful without gaining uncontrolled reach. We've already looked at why agents are risky, how to model threats, and how least privilege and validation tighten tool permissions. The next layer is runtime isolation. Even approved tool calls need boundaries, because harmful behavior can still happen during execution. Sandboxing is the containment layer we'll rely on before moving into prompt injection. An agent can produce an action that looks valid, a command has the right fields, an API call matches the schema, or a file path is well-formed. But valid in form does not mean safe in effect. At runtime, that action may delete data, expose secrets, overload a service, or reach systems it should never touch. Sandboxing adds an execution boundary around those actions. It limits resources, isolates files, controls network access, caps runtime, and records what happened. The goal is not to fully trust the agent. It is to make failure survivable. Think of a sandbox as a contract around any work an agent runs. It says, this process may use only this much compute, see only these files, talk only to these network destinations, and act only with this temporary identity. That matters because agent-generated tasks can be useful, but they are not inherently trustworthy. If code loops, compute limits stop it. If it probes the machine, file system rules contain it. If it calls out, network controls restrict and record it. And if credentials leak, scoped, short-lived identity keeps the blast radius small. When an agent writes code or proposes a shell command, treat that output as untrusted until proven otherwise. A safer pattern is to route execution through a policy check, then run it inside a disposable sandbox, such as a lockdown container, microVM, or restricted runtime. Keep the image minimal, with only the tools the task needs, and remove dangerous privileges. No host shell, no broad mounts, no Docker socket, and no privileged mode. After the run, filter the output, return only approved results, and destroy the environment so nothing persists. Containers can provide useful isolation, but their default settings are often too trusting. Treat every container as something that must be deliberately hardened. Run the workload as a non-root user, then remove Linux capabilities it does not need. Add runtime enforcement with seccomp, AppArmor, SELinux, or an equivalent profile. Make the root file system read-only and allow writes only in controlled temporary paths. Block privileged mode, host namespace sharing, broad IPC, and sensitive host mounts. The goal is simple. Compromise inside the container should not become control of the host. File system access should follow the same principle as network access. Give the agent only what the task requires. Broad host mounts are dangerous because they may expose secrets, production configuration, source code, or user data the agent never needed. A safer setup is a minimal workspace with reference files mounted read-only, plus a separate writable scratch area for generated outputs. That prevents accidental modification and limits persistent artifacts. Before anything leaves the workspace, scan and filter it, because outputs can still contain copied secrets, hidden metadata, or sensitive intermediate data. Resource controls turn untrusted or expensive work into bounded work. Every operation that can run, allocate, write, spawn, or call outward should have a clear ceiling. Runtime, CPU, memory, disk, files, processes, network calls, concurrent jobs, and output size. When a limit is reached, the system should stop or degrade the task safely, not keep trying indefinitely. These controls reduce denial of service risk, prevent surprise cloud bills, and protect shared infrastructure. Repeated limit failures are also evidence. Treat them as security signals that may indicate probing, abuse, or a broken integration. Outbound access is a controlled privilege, not a default capability. When agent-run code tries to reach the internet, the request should pass through an egress proxy and policy engine before anything leaves the sandbox. A safe baseline is default deny. Then allow only the domains, IPs, protocols, and APIs the task actually needs. Also, block destinations that should never be reachable. Private networks, cloud metadata services, internal admin panels, and unknown domains. Log every attempt, including denials, payload size, and frequency. So suspicious behavior becomes visible quickly. Network allow list should be narrow and specific. Permit only the exact domains and endpoints a tool needs, such as a specific weather API, and avoid broad wildcards like star.com. Then validate each request, not just the hostname. Check the protocol, method, headers, destination format, and payload size. Block common escape paths as well. DNS rebinding, redirects to untrusted sites, and encoded URLs that hide the real destination. The rule of thumb is simple. The tool's purpose defines its network reach. Rather than letting each sandbox manage its own connections, route all outbound traffic through an authenticated egress proxy. That proxy becomes the control point. It verifies identity, checks policy, blocks disallowed destinations, and forwards only approved requests. The benefit is consistency. Policies live centrally, not scattered across worker code. The proxy also creates an audit trail: domain, path, method, status, payload size, and timing. Sensitive fields should be redacted or hashed, so logs remain useful for investigation without exposing secrets. This makes outbound behavior observable, governable, and auditable. Isolation is not only for code execution. Imagine an analytics agent that needs customer trends. If it connects with a broad database role, a bad prompt could push it to read sensitive rows, call stored procedures, or run expensive queries. Safer design starts with read-only access, then narrows tables, columns, rows, and query time. The same idea applies to internal APIs. Agents should call approved routes through a service gateway using scoped, time-bound credentials. Undocumented admin or debug endpoints should be invisible and unreachable. Least privilege becomes the default, not an afterthought. Fail closed means uncertainty is treated as risk, not permission. If the policy engine cannot decide, if credentials cannot be narrowed, or if the proxy is down, the request stops there. The system should never helpfully run the command locally, reuse broad credentials, or bypass isolation to keep the workflow moving. Denial is only half the pattern. Return a clear, non-sensitive error that tells the user what to try next, and log the technical details for review, debugging, and incident response. Retries should be controlled decisions, not automatic persistence. Set a hard retry limit, use exponential backoff, and restrict repeated execution of high-risk actions like payments, data exports, or permission changes. Most importantly, never let the agent respond to a sandbox, validation, or network denial failure by relaxing its constraints. If sensitive data or privileged systems are involved, repeated failures should escalate to human review. Log patterns like blocked egress, quota exhaustion, and permission failures because they may signal probing, misuse, or an active attack. The big takeaway is this: least privilege only works when it is enforced at runtime. Sandboxes limit what agents can run, read, reach, and authenticate as. Egress controls reduce exfiltration paths. Fail-closed behavior prevents quiet bypasses and flags suspicious retries. With execution contained, we're ready to study how prompt injection and data exfiltration attacks try to misuse agent tools.